Okay, so this section 6.8, we're skipping section 6.7. 6.8 is about something called L'Hôpital's rule. So this is spelled L apostrophe hospital, okay? But it's pronounced L'Hôpital, you know, like, because French. So L'Hôpital is how it's pronounced, L'Hôpital. L'Hôpital's rule. So this is a rule that will allow us to evaluate some certain kind of limits. So let's just consider the following limit here. So the limit as x goes to 1 of the natural log of x over x minus 1. Okay. So prior to understanding L'Hôpital's rule, we don't really have any way of evaluating this except to maybe look at its graph. The thing to notice is that this seems to go to, so as x goes to 1, the log of x goes to the log of 1, which is 0, and x minus 1 also goes to, goes to 1 minus 1, which is 0. So this limit is approaching something that looks like 0 over 0. So how do we make sense of this at all, right? You can't divide by 0, and so we need a technique for doing this. Similarly, we might see something like, I don't know, x squared minus x over x squared minus 1. Okay, this is also going to 0. The numerator goes to 0 as x goes to 1, because it just goes to 1 squared minus 1, and the denominator goes to 0 as well, because it goes to 1 squared minus 1. So how do we make sense of that? How do we make sense of something like this limit? So the limit as x goes to 0 of sine of x over x, okay? Well, the denominator goes to 0, and the numerator, as x approaches 0, also goes to 0, because sine of 0 is 0. So this is another 0 over 0 limit. We could expand this a little bit. We could say, well, what about as x goes to infinity of the natural log of x over x minus 1? Okay. Here, log of x climbs without bounds, so this is infinity, and x minus 1 gets larger and larger as x goes to infinity, so this goes to infinity. So again, we have a situation where we can't make any sense of this. These are called indeterminate forms, okay? The indeterminate forms. These limits of the form 0 over 0 and infinity over infinity. And so L'Hôpital's rule is about dealing with indeterminate forms. So here's what L'Hôpital's rule says. So it says that if f and g are two functions that are differentiable, so we can take their derivatives. So if f and g are differentiable, and g prime of x is not equal to 0 near x is equal to a, then we have two situations. If f goes to 0 and g goes to 0 as x goes to a, or, okay, so this is one situation where the top and the bottom of this fraction both go to 0, or 2, if f goes to plus, let's say plus or minus infinity, and g goes to plus or minus infinity as x goes to a, okay, and so a is allowed to be infinity in this case, then this L'Hôpital's rule says we can evaluate the limit, so the limit of f of x over g of x as x goes to a. Is this showing up at the bottom of the screen? It is, okay. Then we can evaluate this limit by substituting f and g by their derivatives. So we take the limit as x goes to a of f prime of x over g prime of x. Okay, so this is what L'Hôpital's rule says. Okay, it says that if you've got two functions in a fraction and you're taking a limit, then if both functions go to 0 or if both functions go to infinity, then you can evaluate the limit of their quotient by taking the limit of the quotient of their derivatives. Okay, so fairly straightforward rule, especially once you've seen it in practice a couple of times. So let's see it in practice a couple of times here. I think probably best to go through some of the examples that we just pointed out. So the first example was the limit as x goes to 1 of log of x over x minus 1. Okay, so this certainly is going to 0 over 0. So L'Hopital's rule applies. Okay, so this is part of calculating using a limit using L'Hopital's rule is to observe that it applies. If it doesn't apply, you don't want to use it. So we can compute this limit by taking the limit as x goes to 1 of the derivatives of these two. Okay, so the derivative of log of x is 1 over x, and that's an equal sign, by the way, and the derivative of x minus 1 is just 1. Okay, so this is the limit of 1 over x over 1 as x goes to 1. 1, and both of these, the numerator and the denominator, are defined now at x equals 1, so we can just plug in. So if you plug in, you just get 1 over 1 over 1, so this is 1. Okay, so this limit, even though it appears to go to 0 over 0, actually approaches 1, and you would see this if you graphed this function. The graph would pass through the height 1 if you graphed this function. All right, let's do another one of these examples. So we had this limit as x goes to 0 of sine of x over x. Okay, again, this goes to 0 over 0, so L'Hopital's rule applies. Okay, we have to check that. And so we can compute this limit by taking the limit of the ratio of these derivatives. Derivative of sine of x is cosine of x, and the derivative of x is just 1. Now, 0 is a number that's totally fine to plug into cosine. When you plug 0 in for cosine, you get 1. And so this is just 1 over 1. So the limit is 1. Okay? And in fact, if you graph this function, it will pass through the height 1. Graph this function sine of x over x looks it's a little bit like this. Right around x equals 0. It passes through the point, the height 1. Okay, so if you graphed this function, you would see this behavior and you would guess the limit was 1, but you can only verify it using L'Hopital's rule. Okay, another example. How about this this example we used where we had x squared minus x over x squared minus 1. So this was going to 0 over 0. Again, L'Hopital's rule. And so we can compute this by taking the limit of the ratio of the derivatives. Derivative of this is 2x minus 1, and the derivative of the denominator is just 2x. When you plug 1 into this, you don't get 0 in either of the numerator or the denominator. In particular, you don't get it in the denominator, and you get 1/2. So 1/2 is the limit of this ratio of polynomials. Very good. Maybe another example that we listed on the first page. This was the limit as x goes to infinity of log of x over x minus 1. We observed before that this was going to infinity over infinity, so L'Hopital's rule applies. And so we can compute this. The limit as x goes to infinity of the derivative of log is 1 over x, and the derivative of x minus 1 is just 1. So now, what's happening to this fraction? Well, 1 stays the same as x goes to infinity, and the numerator here goes to 1 over something that's getting larger and larger. So the numerator goes to 0 in this case. So this is 0 over 1, which is 0. So this limit approaches 0 as x goes to infinity. All right, I guess we'll keep this page. Let's do another example. L'Hopital's rule is a very, very useful formula for computing limits of things. So how about the limit as x goes to infinity of e to the x over x squared? Okay, so we know that the exponential graph certainly goes to infinity when its input goes to infinity, and x squared, of course, goes to infinity as well. So this is L'Hopital's rule applies in this case, and so we can compute this using the ratio of the derivatives. So the derivative of e to the x is just e to the x. It's its own derivative. The derivative of the denominator is 2x. And again, we see, okay, e to the x goes to infinity. 2x also goes to infinity as x goes to infinity. So we're back where we started But the nice thing about this is that L'Hopital's rule applies again. And so you can take the ratio of the derivative of these two functions. So you get the limit as x goes to infinity. E to the x is its own derivative, and the derivative of 2x is just 2. And now we get something that we can actually work with. This is infinity over 2, which is infinity, of course. So that is the answer. So this limit goes to is infinity. This function, the ratio of this function goes to infinity. In fact, you could put any number you like in the exponent here in this question, and the answer would be the same. E to the x always beats any polynomial in terms of the limit. So e to the x beats any polynomial in an infinite limit. Any polynomial. You would just have to, notice we had to use L'Hopital's rule twice to get that. If that were x to the 7, we'd have to use L'Hopital's rule 7 times before we got to a point like this. Okay, so very good. That's an example of L'Hopital's rule applied twice. Let's try another example. So this is the limit as x goes to infinity of the log of x divided by the cubed root of x. Okay. So this, again, log x goes to infinity. And this cubed root of x, that's just x to the 1/3. That also approaches infinity as x goes to infinity. So L'Hopital's rule applies here, so we can use it. So let's use it. X goes to infinity. 1 over x is the derivative of log. The derivative of x to the 1/3 is 1/3 x to the minus 2/3. Okay. All right. So this is something that has to be simplified before we can investigate what's going on. So let's take. I want to write all of the x's as positive powers. So to do that, this 1 over x in the numerator becomes an x in the denominator. That 1/3 in the denominator becomes a 3 up here, and x to the 2/3, minus 2/3 in the denominator is x to the 2/3 in the numerator. Now, we just cancel powers. There's 2/3 of x here, there's 1 of x here, so that leaves us with 1/3 of an x down in the denominator. That's just canceling the powers here. And now, this is 3, and x to the 1/3 goes to infinity, so this is going to 3 over infinity, which is 0. Okay, so the limit of this expression, even though the numerator and the denominator appear to both be getting very large, in fact, this limit is 0. And this is because log of x, does not get very, very big at the same rate that x to the 1/3 gets very, very big. So the denominator, in some sense, is getting bigger faster than log, and so the limit ends up being 0. All right, let's do an example where we don't use L'Hopital's rule. So here's a limit. Let's do x goes to pi from the left-hand side of sine of x over 1 minus cosine of x. Okay. Now the thing to keep in mind is that this does not, in fact, go to an indeterminate form. Sine of pi of x, or sine of pi, is equal to 0, and cosine of pi is equal to minus 1. So this is 1 minus minus 1, which is 0 over 2, okay? Which is just 0, right? So that's the answer. Whenever we can plug in the limiting value and get a real number, then we can do that. Whenever we're taking the limit of a fraction of continuous functions and this point works inside of here, then that's fine. So L'Hopital's rule does not apply here. So no L'Hopital's rule. So you don't always have to use it, and it's important to check as you go through this that we even need to use L'Hopital's rule. All right, question. A new type of example here. Pardon me. What about x goes to 0 from the right of the quantity x times log of x? Okay. So what is this going to? So this seems to be going to, as x goes to 0, that goes to 0. And as x goes to 0, log of x goes to minus infinity. Okay. So this expression in here, when we take x closer to 0, is going to something close to 0 times something very, very big and negative. So what wins? I mean, is it going to be 0? Is it going to be minus infinity? Is it going to be something in between? We just don't know, right? But this isn't an indeterminate form the way that our other expressions have been, and so we have to rewrite this in a new way. What I'm showing you is a trick here. We get let's write. How about we write log of x in the top, and I'm gonna just do a little. This is a trick. I'm going to write x in the numerator as 1 over x in the denominator. Okay. Now let's take a look at this. What's happening here? This is going to minus infinity in the top, and then the bottom, as x goes to 0, 1 over x goes to infinity. The smaller you make the denominator of this fraction in the bottom here, the larger that becomes. So this is approaching infinity in the denominator. And now it looks like an indeterminate form. So now we can use L'Hopital's rule. So check, L'Hopital's rule applies. So let's do that. So we take the limit as x goes to 0 from the right. Derivative of log of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. Okay, right? That's x to the minus 1, so that's its derivative. And then if we simplify this, we get the limit as x goes to 0 from the right. We have 1x in the denominator, that x comes down here, and this minus 1 over x squared becomes a minus x squared in the top. So we get the limit as x goes to 0 from the right of minus x, and so this just equals to 0. So in fact, this x here going to 0 beat this log x here going to minus infinity. So x went to 0 faster than log x went to minus infinity. So this limit, actually, this function, if you graphed it, would actually pass through 0 as its graph would pass through 0. So that's sort of a trick involved in computing limits. So this is taking something 0 times infinity and writing one of these pieces as 1 over itself in the denominator. Okay, that's a standard trick for some of these questions. So keep that in mind. Okay. Now I want to look at a new kind of example. So the limit. Let's try the limit as x goes to 0. Let's say from the right of x raised to the x power. Okay. So what's going on here? This is going to 0 to the 0 power. Okay, how do we make sense of that in any way whatsoever? Remember, we usually think that 0 to anything equals 0. On the other hand, usually when we raise something to the 0 power, we get 1. So which is it? What's going to happen with this? So here's the trick for this. So I want to rewrite x to the x as, I want to take its log here. So if we take the log of x to the x, so this is a little trick. If we write x to the log, or log x to the x, this is equal to x times log x. So we have, we've just used the power of logs where we know something to an exponent inside of a log, you can bring the exponent down. So that's all we've done. So I want you to notice here that what this means that if we take e and raise e to both sides of this, well, one side we're going to get e to the x log x. And on the other side, we will get e to the log of this stuff, so that will just be that because e and log cancel each other out. So we're thinking of rewriting x to the x as e raised to the x log x. Okay, so think about this. This was a little trick. We wrote this. We took the log of this and wrote it in that way. And now, in order to take the limit of this, so the limit of x to the x as x goes to 0, that should be the same thing as the limit as x goes to 0 of e to the x log x, right? Same function, so the same limit here. But the key to this is that we can figure out what this is by passing this limit into the exponent here, because the exponential function is continuous. So exponential function is continuous. Okay? And anytime the exponential function is continuous, that means that you can pass the limit into the numerator, or I'm sorry, into the power, like this. So we really are just interested in e to whatever this limit is, okay? But we just calculated what this limit was. We calculated the, let's see, where was the previous page? The limit as x goes to 0 of x times log x. We just computed it here. The limit as x goes to 0 of x times log x, we got 0. So we're going to use that in order to solve the rest of this problem. It's really, we're basically done. E raised to the, this is 0, so we get 1. Okay, so this is the answer. X to the x approaches 1 as x goes to 0. Okay, and this is the trick for doing it. Okay, so in general, if you're looking at the limit as x goes to a of, let's say, a function raised to a function power, okay? And if this goes to any one of the following 3 scenarios, 0 to the 0, infinity to the 0, or 1 to the plus or minus infinity. These are also called indeterminate forms. Indeterminate forms. Okay. And the trick in all of these is to write f of x raised to the g of x power as e to the power g of x times the natural log of f of x. So if you think very carefully about this, this is totally true, right? G of x, because that's a log right there, you can move that g into the power of f there, and then you will be left with e to the log of f to the g, which is that, right? Because e's and logs will cancel each other out. So think about this. This is true. Okay? Convince yourself using the properties of e's and logs that this is a true statement. And then, in order to evaluate the limit, in order to evaluate the limit as x goes to a of f of x raised to the g of x power, we just evaluate, we do the same trick as before, we write e, and we pass the limit into the exponent here. G of x log f of x, like this. So we just evaluate this limit, and then we raise, whatever that number is, we raise e to that power, okay? So we'll definitely go through examples like this in class. This is not something that I want to do much more of on the video here, but this can be done in class. And once we've done a couple of them, I think you guys will not think that they are so bad. All right.